Buen dia, chemistry class. All right, so I'm going to make 2 videos to answer these questions that I assigned last week because I can't fit them all on the board at one time. And because they're harder, so I need to explain more, okay? So remember, we were talking about light and quantized energy. And we're going to talk about, remember there was the wave nature of light, the particle nature of light, and then the way they both work together, okay? So our first question number 8, was compare the dual nature of light. Remember, compare the dual nature of light. So visible light is a form of electromagnetic radiation. Remember, that's the wave theory. Electromagnetic radiation, waves, okay? And then it can be gained and lost in particles known as quantum. A quantum is the minimum amount of energy that an atom can gain or lose. It's a quantum. That's the particle theory, right? And the dual nature states that a beam, well, Einstein came up with this, remember? A beam of bundles of energy called photons is the dual nature of light. A beam of bundles of energy. So it's the wave. The wave has photons in it. The wave has quantum in it, okay? And what is a photon? A photon is a massless particle that carries a quantum of energy. So basically, if you were to compare the dual nature of light, I don't exactly care. I just talk about the wave nature and the particle nature and then how they work together and like what that means. So you have the wave nature, right? You have the particle nature where energy is gained or lost in quantum, okay, right? And then the dual nature is a beam of bundles of energy called photons. So that's how they work together, okay? Let's look at number 9. Number 9, describe the phenomena that can be explained only by the particle model of light. Now there is a couple, but this is the main one, okay? The photoelectric effect. So if you remember, I talked about this last time, right? You have the incident beam of light where it hits the metal. And if it's above a certain frequency, then electrons get ejected from the metal. That's the photoelectron effect, okay? But remember, the reason this is a thing, so the wave nature of light, the wave theory, wave model predicted that with enough time, low energy, low frequency light would accumulate enough energy to eject photoelectrons from a metal. So the wave theory said that it didn't matter what kind of light there was. If it shined on the metal long enough, it would eject in a photoelectron. In reality, that is not true. That is why particle nature can explain this theory, can explain this phenomena, but wave theory can't, because the wave, it doesn't matter how long the light shines on it. In reality, the light must be above a certain frequency. Remember, it must be above a certain frequency in order to eject a photoelectron. So if the light's above a certain frequency, then the electrons get excited and one is ejected. But if it's below, nothing will happen no matter how long the light shines. So the higher the frequency is of the light that hits it, the higher energy the electrons will be ejected. And if the light is more intense, as long as the light's at above a certain frequency, the higher intensity of the light, the more photoelectrons get ejected. So the light is brighter and above the right frequency, more electrons will be ejected versus if it's dimmer. Okay? But this is a theory. So the photoelectron effect cannot be explained by the wave nature of light, wave theory of light. Remember? It said, so you can, no matter how long you shine light on this piece of metal, if it's not above a certain frequency, electrons will never get ejected. Okay? Alright. Number 10. Compare and contrast continuous spectrum and emission spectrum. Okay, I didn't talk about this actually in the videos last week because we talked about lots of other things. This is pretty important though, okay? So remember, continuous spectrum of light, I tried to draw it, but it wasn't very good. But the continuous spectrum of light has all the wavelengths with no gaps. So it's just, remember all the colors. Visible light, the white light spectrum, that's the continuous spectrum. Has Roy G. Biv, red, orange, violet, green, Roy G. Biv, blue, violet, red, orange, yellow. You get the idea. It has all the colors in it, okay? But an emission spectrum is what happens when an electron in an excited state moves to lower energy, and energy gets emitted as photons, okay? So it's different for every element. So basically what that means is if you heat up, if you do the flame test for a certain element, you only will see lines of light where the photons are emitted from. Okay, so an example of that. So it's different for every single element. So an example of that here, we have hydrogen's atomic emission spectrum. This is also an EDI system if you want to look at it. It's a way better photo than what I drew because there's different colors here. Okay, but hydrogen's atomic emission spectrum emits light at oh, it's getting windy over here, sorry. Emits light at 410 nanometers, 434 nanometers, 486 nanometers, 656 nanometers, but nowhere else. There's no light in the rest of the whole spectrum for hydrogen, okay? So that is the difference. So in helium, if you were to do this test for helium, then it would emit light at only certain slits of different slits of light. Different slits of light in the spectrum, but it would be different than hydrogen, versus the continuous spectrum is all the light is emitted. The atomic emission spectrum is only certain slits of light are emitted, and the slits that are emitted are different for every atom, or different for every element, sorry. So you can test different elements and see which elements they are based off of where they emit light at, which slits they emit light at. So the big difference between these two, yes, they both are spectrums of light, but the continuous spectrum shows continuous light, has all the colors, all the way, like the whole range, right? But the emission spectrum doesn't have the whole range. It only emits at certain spots, which is different for every element. Okay, that's how you compare and contrast that. Okay, so emission spectrum is important because you can test different elements and see what they are. Here's number 11, and then I'll make my video for the next one. Okay, number 11. Oh, let me get my notes. Okay. Employ quantum theory to assess. Employ quantum theory to assess the amount of energy that matter gains and loses. Okay. So quantum theory. This basically is saying, how does quantum theory explain how energy is gained or lost? And if you remember, so this is, I don't know, whoever wrote these questions worded them very confusing. Okay. But, so quantum theory, if you remember, a single quantum is the minimum amount of energy that can be lost or gained by an atom. Remember that? So matter can only gain or lose energy in multiples of the quantum. If you remember, so a quantum is a packet of energy. And you can only gain or lose in one packet. You can't gain or lose a half a packet. So we have 1 HV, 2 HV, 3 HV. Remember me talking about this before, right? You can't have 1.13, 1.5, 1.75. It only is in whole packets. Okay? So that is how energy is explained using quantum theory. You can gain a packet, you can lose a packet, but it must be a whole packet. You can't gain or lose a part of a packet. Okay? So that's how you can explain it. Matter can only gain or lose energy in multiples of the quantum. And a quantum is the minimum amount of energy that an atom can gain or lose. Okay? So atom gains or loses energy, it's only in a packet of quantum. A quantum packet. Okay? It can gain a whole packet, it can lose a whole packet. Sorry, gain a whole packet, lose a whole packet. But it can't gain or lose a half a packet. Okay? Alright, I'm going to answer the next 3 questions in the next video, so stay tuned.